Okay. So now that's out of the way. Let me see now. Okay, so you said buffer, you said?
Yeah.
Okay, I'm just going to pull something from Google. Let me see here. Okay, here are some questions here. Let's see what we have here. This is from Arkansas State University, Department of Physics and Chemistry. It says, okay, in fact, you know what? Let me see, let me look at these here. Yeah, click. But these are rather simple. Let me do this one. I mean, for these here, it just seems as if all you need to do is plug the numbers into the Henderson-Hasselbalch equation.
Yeah.
Let me see here. Oh, shoot. How can I paste onto this here? For some reason, it's not. Let me try this again. It's not allowing me to paste onto that. Let me see if I can paste it onto this one here. Hope it's not allowing me to. All right. I guess I have to use the writing tools provided by Zoom to do this one. So let me, oops, sorry. Let me go back to this here. Then I use the writing tool. Okay, so if I were to do this question here, I'm going to see if I can do it down here. I'm basically going to use the Henderson-Hasselbalch equation, which I think is actually provided in the handouts, right? Which is pH is equal to minus log, or I should say pH is equal to pKa, which is minus log of Ka, but I'm just going to use pKa here, plus log of the concentration of the conjugate base divided by the concentration of the weak acid of that conjugate base, right? So my pKa is minus log of Ka, and they gave you the Ka value here, which is 7.1 times 10 to the minus 4 plus log of the concentration of the A minus. Now the A minus in this case would be the fluoride ion, which is provided by the sodium fluoride, and they gave the molarity as 0.70, and then we divide that by the concentration of the weak acid, which is 0.30. And that's basically it. Let me get my calculator. So I'm going to do the 0.7 divided by 0.3 and then find the log of that, and that part works out to be equal to 0.37. And then for this part, 7.1 times 10 to the minus 4, the log of that would be 3.15. And so 3.15 plus 0.37. So according to my calculations, this works out to be equal to 3.52. So that's basically that. Now, you can have some more challenging buffer questions where they ask you to determine the pH before you add a certain amount of acid or base. And let me see if I can find an example of that. But before I do that, any questions about this so far? Any questions?
Nope, that was good.
Okay, all right. Let me see if I can find a more challenging one. Let me clear this first. And okay, that. Okay, let me see what this one is saying. Okay, this is a buffer. Let me see here. A buffer solution contains this and this. If 0.0464 moles of potassium hydroxide are added to this amount of buffer. What is it? Okay, let's do this one here. I wish I could, you know what? I think I know what I'm going to do. Let me use a Word document. So let me go to files and let me see here. Okay, let me go back to this here and let me copy this here and paste it onto the Word document here. Okay, so that's a question. Now, how do I do? Oh, right. Okay, now we're in business. All right. Check to make sure this works. Okay, good. All right. So this question says you're given this molarity of potassium bicarbonate and this molarity of sodium carbonate. All right. So basically, this would be the weak acid because this contains HCO3 minus, and this would be containing the conjugate base of the weak acid because that is CO3 2 minus, right? Now the question continues to say if 0.464 moles of potassium hydroxide is added to 225 mils of this buffer, what is the pH of the resulting solution? Okay, so basically you're going to start off with 225, whoops, let me do this here, 225.0 mils of the buffer, right? What we need to do is find out the number of moles of HCO3 minus present and the number of moles of CO3 2 minus present in this volume of the solution. Let me erase this here. So the first thing I would do is, for the number of moles of the bicarbonate, I would convert the volume first to liters, and then I'll multiply by the molarity, which is 0.384 moles per liter. And then I would work this out. So let me do that. And again, please do these calculations along with me because I could be wrong in my work. So when I worked this out, I got 0. Oh, shoot. I got 0.0864 moles, all right? And I'm going to do the same thing with the carbonate ion, same volume, because they're both in the same solution. Convert to liters, like I did above. But I'm going to multiply by the different molarity, which is 0.239. So I'm going to put 0.239 moles over 1 liter. And then I'm going to do the number crunching for that one, 225 times 10 to the minus 3 times 0.239. And according to my calculation, this works out to be equal to 0.0538 moles, all right? So the next thing I'm going to do now is write down the reaction of the weak acid, which is HCO3 minus, plus water to form H0 plus CO3 2 minus, all right? And then now I'll set up an ice table where the initial amounts of the bicarbonate and oh no, I'm sorry. I just realized something. We're adding something to it. We're adding the potassium hydroxide. So it says, okay, so we need to have a reaction, an equation for the reaction when potassium hydroxide is added to the buffer. So the question now becomes, and this is usually where students screw up when they usually have difficulty interpreting what the question is asking for. The question says you're adding potassium hydroxide. So what you have to figure out is which of the two components the potassium hydroxide will react with. Now, potassium hydroxide is a base, which means that it's going to react with the acid component, which would be the bicarbonate, right? So the equation that I should have written here is the reaction between the bicarbonate ion and the hydroxide ion from the potassium hydroxide, and the product of, or the products of that reaction would be the carbonate ion and water, right? So initially, the amount of the bicarbonate is what we calculated here. So I'm going to put 0.0864 moles. And the hydroxide, the amount they gave us is 0.0464 moles. And then for the carbonate, we calculated that amount to be equal to 0.0538 moles, all right? So those are the initial values. We don't need to, of course, concern ourselves with water. And then we have to ask ourselves what the change for each of these will be. Now, because this reaction goes to completion, that means that the limiting reactant will be used up. And we can tell which is the limiting reactant easily because it's a 1-to-1 mole ratio between these two. So therefore, the limiting reactant in this case would be the hydroxide ion. So all of it would be used up.
I have a quick question about that.
Yes, ma'am.
If it wasn't a 1-to-1 reaction, like let's say it was 2 OH or something, would that change anything?
Exactly, it would, because now you'd have to figure out which one is the limiting reactant by looking at the mole ratio. So for example, and I'm just going to use this as an example, even though it's not the case. Let's say it was a 2-to-1 mole ratio, right? Then basically you have to figure out now, okay, will all of the hydroxide be used up or all of the bicarbonate be used up? In which case, you'd have to say, well, let me do a little thing over here. You'd have to say, well, if 0.864 moles of HCO3, I need more space. All right, tell you what, let me do it down here, but I'm going to erase it. I need more space to do this here. I'm going to do it down here. Okay, so let's say it was 2-to-1, right? 2 hydroxides for 1 bicarbonate. So basically what that means is that if we have 0.0864 moles of bicarbonate, if the mole ratio was 2-to-1, then that means that for every 2 moles of hydroxide, there's 1 mole of bicarbonate, right? Which would mean that this becomes 0.0, what is 2 times that? So 2 times 0.0864, according to my calculation, works out to be equal to 0.173 moles, right? Of OH minus, right? So what that tells me is that because this amount of bicarbonate requires this much hydroxide ions, which is greater than the amount that is there, that tells me that this would be the limiting reactant still, all right? Because the amount of hydroxide, the amount of bicarbonate here that is used up, or that would have to be used up, needs more than the 0.0464 moles of the hydroxide that is originally present. So basically you have to take that into account, the mole ratio, in order to determine which is the limiting reactant. And then once you determine which is the limiting reactant, then you can go ahead to examine the changes, all right? Okay. But so I don't know if if you understood what I just said here.
So basically, because that 0.173
is greater than the 0.0464. So what that tells us is that you don't have enough hydroxide to use up all of the bicarbonate. So that tells us that the hydroxide would be the limiting reactant in this case. If it was 2-to-1, remember, we're just assuming it's 2-to-1, which it is not. All right. You see, when it's 1-to-1, it's very easy. You just look at the amounts. The one in lower amount would be the limiting reactant. But when it's 2-to-1 or 3-to-2 or something like that, then you have to take an extra step to determine which is the limiting reactant. And this is something you should have met in your introductory chemistry. All right, so if you understand this, let me go back to the table here. Let me erase this here. Okay, so as I said before, let me erase this. This is not 2, this is 1. Okay, so as I said before, because of the 1-to-1 ratio, and because the amount of hydroxide ions is less than that of the bicarbonate mole-wise, we can therefore assume that all of this will be used up and an equivalent amount of the bicarbonate will react as well. And over here, the amount of carbonate produced would be the same, 0.0464 moles. So therefore, at the end of this reaction, we can find out, well, this will be 0, of course, and then we can, let me get my calculator here, and find what would be the amount of bicarbonate left, which would be 0.0864 minus 0.0464. And according to my calculations, this works out to be equal to 0.04, how many decimal places? 1, 2, 3. Okay, so 2 more zeros, all right? And then over here, it will be 0.0538 plus 0.0464. And according to my calculation, this works out to be 0.1002, all right, moles. So these are the moles of bicarbonate and carbonate remaining at the end of this reaction. All right, so let me scroll back up here because I need to be reminded of something from the question. So it says that, okay, it says it's asking for the pH, and it also says assume that the volume does not change upon addition of potassium hydroxide. So the volume we're working with here is the 225 mils. So what we need to do now is find the concentration, the concentration of both the bicarbonate and the carbonate. So in the case of the bicarbonate, it's 0.0400 moles divided by the volume, which is 225.0 mils, which we have to convert to liters. So 1 liter over 1,000 mils. And let's see what that gives, 0.0400 divided by 225, which itself is divided by 1,000. Okay, so according to my calculation, I got 0.1, how many sig figs? 3 sig figs, so 0.178 M. And then I do a similar calculation for the carbonate. In that case, it's the moles, which is 0.1002 moles divided by 225.0 mils. And again, we convert to liters. And let's see what that gives, 0.1002 divided by 225. Okay, so I got 0.44, how many sig figs? 4 sig figs, so 4453 M, all right? So these are the concentrations that you're going to plug into the Henderson-Hasselbalch equation, which of course is pH is equal to pKa plus log of the concentration of the base, which is the carbonate ion, divided by the concentration of the acid, which is the bicarbonate ion. And then we put the numbers in. So PK is minus log of KA. Did they give the KA value? Hold on. Okay, they didn't give the KA value. So guess what? We have to go to the tables. So let me go here. Okay, where's the tables? Okay, tables. Okay, dissociation constants. Okay, so let me download this. Okay, so this is what we are looking for here. Where's carbonic acid? That's interesting. Oh, here it is, carbonic acid. Now, the Ka value we're looking for is this one right here, right? Because remember, carbonic acid has two hydrogens that it can lose, right? So the first dissociation constant would be here, 4.3 times 10 to the minus 7. And then the second dissociation constant is the 5.6 times 10 to the minus 11, right? So that's the one we're going to use because what we're looking at is the relationship between the bicarbonate and the carbonate. So the answer or the value that we're going to use is 5.6 times 10 to the minus 11. So going back to this here, this will be 5.6. 5.6 times 10 to the minus 11 plus log of the concentration of the carbonate, which is 0.4453 divided by the concentration of the bicarbonate, which is 0.178. And that's it. All you have to do now is the final calculation. So 0.4453 divided by 0.178. And then we find the log of that. And when I did that, I got 0.3. Okay, so this is 365. So this should be 3 decimal places, 398. And then as far as the 5.6 times 10 to the minus 11. Let me find the log of that. Okay, so according to my calculation, that would be 10.25. And then 10.25 plus 0.398. And the answer I got when rounded off to 2 decimal places is 10.65. So that would be the final answer. Okay, any questions about this? Any questions?
No.
Okay. All righty. Okay, any other questions? Any other problems? Issues?
I was wondering if you're gonna do something like this on Monday as well.
What do you mean?
Like a review kind of
Oh,
session.
so
If we
it's
had more
up to you
questions.
guys. It's up to you guys. I mean, if you want to meet up again on Monday to discuss anything, that's fine by me. All up to you guys. I'll be available, that's for sure.
Okay, yeah, because I didn't get to look over everything, but I feel like I would have more questions.
Okay.
But for now, I feel like you've covered most of the problems I've had.
Oh, no problem. And also remember on Friday I have office hours as well. So you can call me on Skype between 12 and 5. And I'm more than willing to help during that time as well. So
Okay.
yeah, just whenever you feel as if you need help, Not help with the test, but help with, understanding stuff.
I have a few like conceptual questions, I guess, about when you make buffer or like when you titrate, like depending on if there's a like strong base, weak acid,
Oh,
or weak,
okay.
like what are the different ways? Like you don't have to necessarily solve the whole problem, but if you could
Right.
just go over the differences and steps to approaching those.
Okay. All right. Very good. So let me go to this here. All right. So titration. So we all know what titration is all about, right? Acid-base titration specifically. All right. So basically, if you think about what you're doing in titration, typically you would have the base in the flask below. No, I'm sorry. You'll have the acid in the flask below. It doesn't matter which really, but most times it's the acid in the flask and the base will be added from the burette, all right? So typically, let's start off with a strong acid, strong base. So let me write this down here. Strong acid being titrated against a strong base, all right? Okay, so the first thing you need to do is find out the moles. Well, so let's say, I think the best way to do this is to use an example. Let's say that the acid is hydrochloric acid and the base is sodium hydroxide, all right? And let's say that the molarity of the hydrochloric acid is 0.100 m, and the same is true for the base, all right? Now, let's say that in the flask, you will have 25.00 mils of the base, of the acid, I'm sorry, right? So the first thing, and you want to find out the pH at different points, all right? So let's say we want to do the pH after adding 10.0 mils, 10.00 mils of the base, right? The first thing I would do after, figuring out all that, the first thing I would do is find the number of moles of each, right? So the number of moles of the acid would be the 25.00 mils converted to liters, and then multiply that by the molarity, which is 0.100 m over 1 liter, moles, I'm sorry, over 1 liter. So let's do that. So that would be 25 multiplied by 0.1. Oops, hold on, I made a mistake here. 25 multiplied by 0.1. Okay, so according to my calculations, this gives 2.50 times 10 to the minus 3 moles, all right? And then I do a similar calculation for the sodium hydroxide. In this case, the volume of sodium hydroxide added is 10.0 mils. Again, I convert that, like before, to liters. And then I multiply that by the molarity, which in this case is again, same thing as before, 0.100 moles over 1 liter. So when I do that calculation, I got 1.00 times 10 to the minus 3 moles, right? Then I set up my ice table by writing first the equation for the reaction to form sodium chloride and water, all right? Initially, the values that I would place here and here would be the values I just calculated for each of those, the sodium hydroxide and the hydrochloric acid. So for the sodium hydroxide, I'm going to put 1.00 times 10 to the minus 3 moles. And here I'm going to put 2.50 times 10 to the minus 3 moles. That will be 0, and we don't need to concern ourselves with water. Again, if you remember what we did in the case of buffers, we have to consider the limiting reactant. Again, it's a 1-to-1 mole ratio, so it's very easy for us to determine that the sodium hydroxide would be the limiting reactant. So all of that would be used up. And here it would be the same amount that will be used up. And here you're going to have plus 1.00 times 10 to the minus 3 of sodium chloride produced. So these are all moles, all right? So at the end of the reaction, you're going to have no sodium hydroxide. You're going to have 2.50 minus 1.00. That gives 1.50 times 10 to the minus 3 moles. And here you're going to have 1.00 times 10 to the minus 3 moles. Now at this juncture, you have to ask yourself, how does what is left affect the pH of the solution? Well, we have hydrochloric acid here, right? 1.50 times 10 to the minus 3 moles of hydrochloric acid. And over here we have sodium chloride. Now the thing about sodium chloride, as you should know, is that the sodium chloride is a product of a strong base and a strong acid. And therefore we know that the sodium chloride will be neutral. It's going to be a neutral salt. So the sodium chloride will have no effect on the pH whatsoever, right? So the only thing that we'll take into account as far as the pH is concerned is the hydrochloric acid. So all we have to do now is calculate the concentration of the hydrochloric acid, which should be equal to the concentration of H plus because hydrochloric acid is a strong acid. And that would be equal to 1.50 times 10 to the minus 3 moles divided by the volume, the total volume. Now, what's the total volume? Remember, you added 25 mils. I'm sorry, you start off with 25 mils of hydrochloric acid and you added 10 mils of sodium hydroxide. So the total volume here is going to be 35.0 mils. That's a sum of 10 plus 25. You have to convert that as well to liters. And then let's see what that gives. So 1.5 times 10 to the minus 3 divided by 35 E3 minus. Okay, so the molarity here is 0.0429 M. And then all we have to do is find the pH, and we all know how to do that. pH should be equal to minus log of 0.0429. And let's see what that gives, 0.0429. We do the log of that. Okay, so according to my calculation, this works out to be equal to 13.68. 13.68. All right. In fact, hold on. This is 13.68. So this is 4 decimal places. That means that this has to be 4 sigfigs. Okay, so that's basically how you do that. All right. So any questions about this? Any questions about this so far?
I'm not sure if I did this different than you, but I got 1.37 as my pH.
Oh, maybe. You know what? Okay, yeah, you're right. My eyes are tricking me. You're right. Let me do this second, 0.0429. Yeah, you're right. I don't know, I missed the decimal point. Or I put the decimal point in the wrong place. So the answer here should be 1.3, actually it should be 1.368. Yeah, okay, my bad. Okay, so that's how you do that, all right? Okay, any questions about the setup? You know, how we go through the steps? Any questions?
Nope.
Okay, now, this is after adding 10 mils. Now, if let's say I were to change the 10 mils to 25 mils, all right? So let me put 25, whoops, wrong pen. 25.00 mils, right? Then what's going to happen is that this will change to 25.00 mils, which would mean that this will change to 2.50 times 10 to the minus 3, which would mean that this will change to 2.50 times 10 to the minus 3. So what does that mean down here? It means that both the sodium hydroxide and the hydrochloric acid would be equal, right? In terms of the moles, right? And therefore, let me erase this so it doesn't look messy. The change will be here. So the change will be minus 2.50 times 10 to the minus 3 moles in both cases. All right. I hear you're going to have plus 2.50 times 10 to the minus 3 moles, right? So that by the end of the reaction, let me choose. No, what am I doing? Let me see here. Whoops. Okay, let me stick to this eraser here. So the result of that will be that you will have, let me rewrite this here. So this will be minus, that will be minus. So you're gonna have no sodium hydroxide left, no hydrochloric acid left, and the only thing that will be left at the end of this reaction would be the sodium chloride, right? And as we said before, the sodium chloride has no effect on the pH because it's a product of a strong acid and a strong base. So what that means is that you don't even need to do any further calculation. Basically, you can come to the conclusion that the pH is going to be equal to 7. It's going to be a neutral solution because at this point, there's no base, there's no acid, there's only sodium chloride. And this is what we call the equivalence point. Let me write this down here. Equivalence point. Right? At the equivalence point, the amount of sodium hydroxide and hydrochloric acid added or mixed together would be stoichiometrically equivalent. In other words, equal number of moles. When that happens, then both of them will be completely used up, and therefore you won't have any sodium hydroxide and hydrochloric acid left at that point. You only have sodium chloride remaining, and that doesn't affect the pH. So therefore the pH is going to be 7, and the solution is going to be neutral. All right. Okay. Any questions about that? Any questions about the calculations at the equivalence point? All right, so now what if the amount of base is higher than 25? So let me change this here to a number that is higher than 25. So let's say the amount of base added is 35.0 mils. Right? Then obviously that means that you're going to change something here. For the base, this will be changed. And this will be changed. So here you're going to have 35.00 mils. And you're going to have 3.50 times 10 to the minus 3 moles in that 35.00 mils. And that means that there'll be changes in the ice table as well. So basically, let me erase this here. Let me put 3.50 times 10 to the minus 3 moles here. So in this case, which would be the limiting reactant? Let me erase all of this here. So which would be the limiting reactant? Will it be the sodium hydroxide or the hydrochloric acid?
The hydrochloric acid.
Exactly. So this is looking kind of messy, but I'll try to work with this. Okay, so you're right, hydrochloric acid. So all of it will be used up. Same amount of sodium hydroxide will be used up. All right, so you're going to end up with, on over here, you're going to have plus 2.50 times 10 to the minus 3, right? So here, the difference between these two will give you 1.00 times 10 to the minus 3. Here, you're going to have 0. And here, you're going to have 2.5, 0 times 10 to the minus 3 moles. Again, the sodium chloride will have no effect on the pH. So basically, the pH would only be affected by the presence of the sodium hydroxide that is remaining. So I'm just going to erase this here to make some more space to do the subsequent calculation. Now, in this case, since we have only hydroxide ions present and we want to find the pH, the way to go about that would be to first find the pOH. So we need the concentration of OH minus first before we can find the pOH. That would be equal to the moles that we just calculated, 1.00 times 10 to the minus 3 moles, divided by the volume. What's the volume? The volume would be the sum of 35 and 25 mils. So that would be what? 60, right? So you're going to put 60.00 mils down here. And then you're going to have 1 liter over 1,000 mils to do the conversion to liters. And let's see what that gives. So that's 1 times 10 to the minus 3 divided by 60. Okay, so according to my calculations, this works out to equal to 0.0167 m. All right, so that would be the concentration of OH minus. So to find the pOH, that would be equal to minus log of 0.0167. So let's see what that gives. 0.0167 log that. Okay, so I got, okay, so this is how many sig figs? 4 decimal places, so it should be 4 sig figs. So this is 1 point, almost made the same mistake again, 1.777, right? So that's a pOH. So therefore the pH, of course, would be 14.00 minus 1.777. Let's see what that gives. Okay, so according to my calculation, this gives 12 point, round off to 2 decimal places, 22. So that would be the pH at that point. All right. Okay, any questions about this?
No questions.
No question. Okay. Now, this is just the strong acid versus strong base, right? We have not even looked at weak acid versus strong base or strong acid versus weak base. And those are more complicated. And the reason why they're more complicated is because, let's say you're dealing with a weak acid. You cannot assume 100% dissociation of a weak acid because by definition, a weak acid undergoes partial dissociation, right? So therefore, certain assumptions that we made here, we cannot make in the case of a weak acid, for example, being titrated versus a strong base. Several elements would still be the same. In fact, the initial part of the calculation will still be the same. In fact, let me give as a weak acid example, let's use acetic acid. Now, I'm not going to write out the entire formula for acetic acid. I'm just going to use HA. All right. So the calculations for the number of moles of the acid would be the same as we did before. Now, what I'm going to do is erase. Let me see here. Let me use, I think we used 10 mils before, right? For the strong base, right? So I'm going to use 10 mils again, but this time, 10 mils for the strong base again. So 10.00 mils, all right? So what we're doing now, excuse me, is a titration of a weak acid versus a strong base. So I'm just going to put here weak acid. Whoops. Weak acid versus a strong base, right? So let me correct our changes here. So this is going to be 10.00 mils. Okay, so that's going to change the final answer here. If I recall, when we did this previously, this is going to be 1.00 times 10 to the minus 3. All right. And so the equation here would pretty much be the same thing. The only difference is that instead of HCl, we're going to use HA here, NaA here, right? So let me erase all this. Let me just erase all this here. Okay, so so this is going to be H2O. All right. So initially, the amount of sodium hydroxide is 1.00 times 10 to the minus 3. The moles of HA would be 2.50 times 10 to the minus 3. You're going to have none of that. The change here, again, the sodium hydroxide would be the limiting reactant, so all of it would be used up. Same amount of HA would be used up as well. And as far as the sodium acetate is concerned, that would be 1.00 times 10 to the minus 3 moles, all right? So at the end of the reaction, you're going to have no sodium hydroxide. You're going to have 1.50 times 10 to the minus 3 acetic acid, moles of acetic acid. And here you're going to have 1.00 times 10 to the minus 3 moles of the sodium acetate. Now, here's where the difference comes in between what we were doing before and what we have to do now. In this case, we know that the sodium acetate is formed from a strong base and a weak acid, right? So therefore, we cannot assume that this has no effect on the pH, all right? So we have to take this into account. Another thing I want to point out here is that the resulting solution will be a mixture of a weak acid and the conjugate base of the acid, all right? And what do we call that?
A buffer solution?
Exactly. And therefore, the equation that we're going to use is to calculate the pH, the Henderson-Hasselbalch equation. Very good. So basically what we need to do at this juncture is find the concentration of both the HA and the sodium acetate. Let's start off with the HA. The concentration of HA would be 1.50 times 10 to the minus 3 moles divided by the volume. What's the volume? 25 plus 10, so that's 35.00 mils. And then we convert that to liters. And let's see what that gives. So that's 1.5 times 10 to the minus 3. And then we divide by 35, divide by 1,000. Okay, so according to my calculation, I got 0.0429 M. And then I do the same thing for the conjugate base, which is 1.00 times 10 to the minus 3 over 35.00. Again, convert to liters, 1 liter over 1,000 mils. And according to my calculations, let's see what this gives. Okay, I got 0.0286 M, all right? And then now I plug it into the Henderson-Hasselbalch equation, which I'm going to squeeze in right here. pH, this is the equation, pH is equal to pKa plus log of conjugate base concentration divided by concentration of the acid, HA. So when I put the numbers in, that would be equal to minus log. Now, if I remember correctly, the Ka for acetic acid is 1.8 times 10 to the minus 5. And then I add that to log of the conjugate base, which is the concentration of the conjugate base, which is 0.0286 M, divided by the concentration of the acid, 0.0429 M. And then we do the number crunching. So that would be 0.0286 divided by 0.0429, and then I do the log of that, and then I add that to the log of 1.8 times 10 to the minus 5. Hold on, wait a minute. I forgot to put the minus sign there. Okay, let me do this again. 0.0286 divided by 0.0429 log, and then I add that to 1.8 times 10 to the minus 5. Okay, so the answer I got is 4.57. Let me see if the correct sig figs. Yes. So the answer would be 4.57. And that's basically how you do that. So as you can see, this is a bit different from a strong acid, strong base situation. And the difference actually comes down to when you've completed the ice table here and you ask yourself, what do I do with these numbers? In this case here, you have to use both of these numbers here. And because we know it's a buffer solution, then we just plug, well, first we have to find the concentrations, and then we plug those values into the Henderson-Hasselbalch equation to get the pH. All right?
I had a question about this.
Yes, ma'am.
If we were supposed to find the pH like the other problem at the equivalence point, would we want, I guess,
Okay, you're talking about in the case of a weak acid versus a strong base?
yes.
Okay, that's another interesting situation here. So let's say we're talking about the equivalence point. So what I'm going to do, to not go through all of this again, I'm going to assume that, let me erase this here, that the amount of base and the amount of acid is the same, right? In terms of the moles, because that's what happens at the equivalence point, right?
Right.
Okay, so let me erase this part right here. So let's say you have done all these calculations here up here, and now you find out that the number of moles of sodium hydroxide is the same as the number of moles of the weak acid. So that means that this will be 2.50 times 10 to the minus 3. That means that here you're going to have minus 2.50 times 10 to the minus 3. And here you're going to have minus 2.50
Quick.
times 10 to the minus 3. So that means that this will be 0 and this will be 0, right? And here you're going to have plus 2.50 times 10 to the minus 3. So here, the final concentration of the moles of the sodium acetate will be 2.50 times 10 to the minus 3, right? Okay, so in this situation here, you'll notice that you have no base, you have no acid. The only thing that you have remaining would be the conjugate base, and this is the amount, all right? So the next step is, or the next question you have to ask yourself is, okay, so how does the A minus, the conjugate base, how does that affect the pH? How does it react with water? Well, and the answer is that because it's a conjugate base, you add it to water, if and when it does react, it's going to act as a base. So how does a base behave when it reacts with a water molecule? Well, it's going to get a proton from the water molecule. That's what bases do, right? So basically, A minus is the base. It's going to get a proton from water, and it's going to be a weak base. And this is the reaction, right? So you have to set up an ice table. But first, before you set up the ice table, you need to find the concentration of the acetate, the conjugate base. So what I'm going to do here is, let me erase this side right here and do a quick calculation over here.
Ask a quick question before you go on.
Yes, ma'am.
Down in that bottom ice chart, you chose to subtract 2.50 times 10 to the negative third from each. Why Because I remember those were originally different numbers. Like one of them was, I think.
Yeah, I was answering your question about the equivalence point. You see, the equivalence point is the point at which the amount of base and amount of acid are stoichiometrically equivalent.
Correct. So you originally had 1.00 times 10 to the
Yeah,
negative
exactly.
third.
That was for the previous example.
Okay, so why did you know, I guess, to choose that number?
2.5?
Yeah.
Because I'm saying that, okay, if this here, let me do this here. If this is the amount of acid that was there originally,
Mhm.
to get to the equivalence point, you're going to need the same amount of base.
Okay, okay.
You see what I'm saying?
Yes.
That's literally what the equivalence point means. It means that the number of moles of the base that was present would be equal to exactly the number of moles of, or I'm sorry, let me back up. The number of moles of acid that was present before would be equal to the number of base that was added to it. Exactly.
That makes sense. Okay.
So that's the equivalence point. All right. So that's why we have these two values here. And of course, they will be used up completely. And the amount of conjugate base form would be the same, 2.50 times 10 to the minus 3, right? So as I was saying, we need to find the concentration of the conjugate base. Oh, shoot, I chose the wrong thing again. The concentration of A minus is what we need to find. And that would be equal to 2.50 times 10 to the minus 3 moles divided by the volume. Now, the question is, what's the volume? It depends on the calculation that was done here. If the concentrations are the same, that means that, what was the volume? What was the original volume of the base? Was it 25?
Let me check.
I think it was 25. But I'll wait for your confirmation.
I thought it was, and maybe this was for the previous problem, but I had 10 milliliters. So I don't know if you changed it to 25 for this example.
Well, what was the volume of the acid?
25.
Okay, so the volume of the acid is 25 mils. Now, the molarity, if I remember correctly, is 0.100 m, right? So if the molarity of the base is the same, that means we're going to need the same volume of the base as the acid. If the molarities are the same and the moles are the same, that means that the volume is the same, which means that the total volume here is going to be 50.00 mils, right? And then we have to do the conversion from milliliters to liters. And then we do the calculation. So that will be 2.5 times 10 to the minus 3 divided by 50. And then my answer I got here is 0.0, how many sig figs? 3 sig figs. So 0.0500 m, right? That concentration is going to go here. You're going to have 0 here, 0 here. Now, in this case, it's an equilibrium system. So the change here, it won't go to completion. We don't know how much of it reacts. So all we can say is that the change here will be minus x, that will be plus x, that will be plus x. So that at equilibrium, you're going to have 0.0500 minus x. Here you're going to have x, here you're going to have x. And then we do the equilibrium constant, the dissociation constant, I should say. Let me erase all this here. This eraser is not very clean. Oops. Oh, I'm erasing what I wrote down, which I'm going to need. Okay, so this is going to be, whoops. This is going to be plus, x, I'm sorry, x and x, right? So because it's a base, we can write down the Kb expression, which is concentration of HA times concentration of OH minus divided by concentration of A minus. And then we put in the terms x times x over 0.0500 minus x. So this is the same thing as x squared over 0.0500 minus x. And then if you remember what we did before, we assume that x is much smaller compared to 0.0500, such that 0.0500 minus x is approximately 0.0500. So that means that this equation simplifies to KB is equal to x squared over 0.0500. And therefore we can find x, which is equal to the square root of KB times 0.0500. Now here's the thing. There's no such thing, or no, let me not be that absolute. In the table that you're given, you will not find the KB of the acetate ion, but you will find the Ka of acetic acid, which is equal to 1.8 times 10 to the minus 5, right? So therefore we know that KB is equal to KW divided by Ka. So we can basically replace KB here with KW divided by Ka times 0.0500. And then we put in the numbers. Let me erase this here. So when we put in the numbers here, that would be 1.00 times 10 to the minus 14 divided by Ka, which is 1.8 times 10 to the minus 5. And then we multiply that by 0.0500. And let's see what that gives. And then I find the square root of that. Okay, so according to, oh, wait a minute, I did something wrong here. I'm not sure what, oh, okay, I think I know what I did wrong. Let me do this again. 1E14 minus divided by 1. And then I multiply by 0.05. And then I find the square root. Okay, so the answer I got here is 5.3 times 10 to the minus 6, right? And of course, you have to find the percent dissociation, which I think is going to be less than 5, just by looking at this number here and comparing it to the 0.005. I think it's going to be less than 5%. So I won't go through that calculation. The only thing I'm going to do now is say that this X is also the same thing as the concentration of OH minus. So all you have to do from here is find the pH. So let me do that up here. So the pH, I'm sorry, the pOH is what we need to find. That would be equal to minus log of 5.3 times 10 to the minus 6. So let's see what that gives. 5.3 times 10 to the minus 6. Find the minus log of that. And I got 5.28 is the pOH. So therefore pH will be equal to 14.00 minus 5.28. And the answer I got would be 8.72. And that's it. So yeah, the calculation at the equivalence point for a weak acid strong base is a bit more complicated because you're going to need 2 ice tables in order to do that calculation. All right. Any questions?
Yeah,
Oh, sorry.
kind of. Okay, so if you're given, you know, however many, like the molarity of the weak acid, and then it gives you the molarity of the strong base. So first you do an ice table.
Well, the first thing you need to do is calculate the moles of each.
Right.
Mhm.
Okay.
And then you set up your ice table for the reaction between the weak acid and the strong base.
Okay, and then if those two moles are different, are you just equivalating the strong base moles to the ones of?
No, if the mole values, after you calculate the moles and they're
Yeah.
different, you place them in an ice table. You determine which one is a limiting reactant,
Okay.
and that one will be the one that is completely used up.
Okay.
And then you figure out, based on that, the amounts of the other products, of the other substances remaining.
Okay.
So basically, once you figure that out, in the last line of the ice table, based on that, you can determine, okay, is this a buffer solution, or is it at the equivalence point, or is it after the equivalence point? Now, if it's a buffer solution, remember now, a buffer solution is one where you have a mixture of both the weak acid and the conjugate base, right?
Right.
So if it's a buffer solution, you know what to do, right? You use the
Yes.
Henderson-Hasselbalch equation, right? Now,
Yes.
if it's at the equivalence point, you do like what I just did, right? You have to basically determine, okay, you determine that there's no acid or base left. The only thing that's left is a conjugate base that is formed. So you'd have to determine the concentration of that, and then you have to write down the equation for the reaction between that conjugate base and the water, and that's where your second ice table will come in. But this time, it will be an equilibrium situation, so it won't go to completion. So you have to write up your ice table, just like you see I did right here, where you have to use X representing the amount of A minus reacting, and you just continue until you get to this line right here. And then you basically set up your KB equation, which is this right here. And you plug in the different terms for the HA, the OH minus, and the A minus, which is what I did right here. And that ultimately led to this equation right here. This should be a 2. Let me make sure. This should be X squared, right?
Okay.
And then, you know, you do like what we did before. You know, you make your assumption and then you solve for X.
And so that answer that you got, that's a pH at the equivalence point?
Exactly, right, exactly.
Okay.
And this highlights another important thing too, is that in the case of an acid, in the case of a strong acid, strong base reaction, the pH at the equivalence point is going to be 7, right? Now, in the case of a weak acid versus a strong base, which is what we did here, the pH is going to be above 7. In this case, it's 8.72.
Okay.
Right? So if you're titrating a strong base versus a weak acid, the pH at the equivalence point would be above 7. Now, if it's a reverse, if it's a strong acid versus a weak base, then the pH would be below 7.
Okay.
Mm-hmm.
Gotcha. Thank you.
Right. So that's basically how that is done.
Okay. I think that's all my questions for today.
All right. Well, if by any chance you have any more questions, you can call me up on Skype until what's class time? 1:10?
1:10, yes.
So I'll be here. You know, if you have any further questions, just call me up on Skype and we can talk.
Okay, thank you so much.
And I also have office hours, as I said before, on Friday from 1 to 5. So again, if you have any questions during that time.
Okay, perfect. Thank you. Have a good day.
Yeah, you too. Take care.
Bye.
All right. Bye.